Okay, trying this video for the third time. Today we're looking at the properties of exponentials, particularly modeling situations that use exponentials so that way we can find some unknowns. While we're doing that, we're going to look at the mathematical constant e briefly, particularly in its role in those modeling situations. Alright, the first application we're going to look at is radioactive half-life. Half-life refers to how long it takes for radioactive substance to decay into a smaller substance. Smaller in this case referring to its atomic number on the periodic table, for those of you that have had some chemistry. Brief description of how this type of radiation works. You have an atom of radioactive substance. Its nucleus, because of how large it is, how much stuff is in there, is unstable, and occasionally that nucleus breaks down and it releases some protons, and because it loses some protons it becomes a different element. For example, certain types of uranium decay, lose some protons, and become lead. That's the way it works. Okay. Now the thing is, you have these protons flying around. And if those protons strike another atom of this radioactive substance, it automatically causes it to break down and release its protons. Remember, these are unstable, so if it's jostled, that makes everything break down again. So now you have multiple protons flying around. And if all of those protons hit other atoms, those atoms break down. And it keeps going and going and going, setting off more and more atoms into a chain reaction. And if there are too many of these atoms and it makes the chain reaction happen too fast, you get an atomic bomb. That's the way it works. However, if you don't have so much of it there, a lot of those protons just fly off into nowhere, and they don't set anything else off. So what happens is, if you have a lot of this together, these chain reactions are going to happen, so the reaction happens faster and things decay at a quicker rate. The less you have, those protons miss everything, all their neighbors, because there aren't as many of them around. And that means the reaction happens quite slower. And because it depends on how much is there in this fashion, it takes just as long for a ton of this radioactive material to break down into half of the ton of that material as it would for an ounce to break down into half an ounce. Okay, that's just because the reaction depends on how much is there. Technetium-99. Technetium is a radioactive element. It's used in a lot of medical procedures, scanning procedures, things like that. It has a half-life of 6 hours. It's one of the reasons why it's used in medicine, is because it breaks down pretty fast. We're starting with 250 milligrams of TC99. How much is left after 75 hours? Alright, if you think about our general exponential equation. Well, in this case, we're going to replace y with m for the mass. A is still the initial value. That's not really going to matter here. B, however, we're looking at how many times half of the substance goes away. So every time that happens, we will have half of what we started with. So the base will always be a half. But for our exponent, you can't just use an x. We need to know how many half-lives go by. Now in this case, we have 75 hours, and half of our thing goes away every 6 hours. So our exponent is going to be the amount of time divided by 6, and that gives you the number of half-lives. Okay. So the amount of mass we have is equal to the initial value, which is 250, times 1/2, to the 75 divided by 6 power. Over my calculator. We get 0.04, rounding it to their hundredth, milligrams of technetium-99 left. That's how this type of radioactive decay works. Look at compounded interest. Compounded interest is when you earn interest on interest you've already earned. All right. Simple interest, which you probably did in junior high, you just have whatever you make. The only interest you make is on the money you deposited. Okay. Now you put money in, or you take money out if it's a credit card, and they charge you off that, and then they charge you off of what they charged you. All right. Now this formula looks kind of complex, but it really breaks down. If you look, it's still the same general thing, but instead of Y, we have a capital A for the amount in the account. Instead of our lowercase a for the initial amount, we have this capital P, stands for the economics term principal, but it's still the same thing. It's the initial amount. It's what you started with. B gets a formula. The base is a formula this time. 1 plus R divided by N. Well, the 1 plus you should recognize from what we did the other day. It's 100% of what we started with plus some more stuff. Now this stuff, R divided by N, R is our interest rate as a decimal. You can't leave it as a percent. You've got to change it to a decimal. And we're dividing that by N, which N is the number of times it's compounded per year. So what that means is, say you have a credit card that charges you 15% interest. So you have some money on the balance. And after a month, they're going to compound it and they're going to figure out what to charge you now. But it's not going to be the full 15% because it's 15% per year. So what you would do is, since credit cards do it every month, N is 12, you take that 15%, 0.15, and divide that by 12, and that's the percent they're going to charge you each month. That's the whole point of this R divided by N. Take what they're going to charge you for the year, divide it by how many times they're going to figure this out each year. Then up in the exponent, as the number of times it's compounded per year, T is the number of years that go by. So this tells you, the exponent tells you the total number of times they're going to figure out your interest. How many times it is compounded, if you will. Alright, so I have an example of that ready to go. How much money will be in an account if $5,000 is invested at 6% annual interest, compounded for 7 years? We're going to do this 2 different ways. First, we're going to find out if they only charge you every year, and then we're going to figure out what happens if they compound this, or not charge you, but how much if they pay you every year, and then how much if they compound it and pay you every month. So yearly, the amount in the account will equal the initial value, which is 5,000, times 1 plus 6%. And if it's every year, it's only once a year. Then once a year times 7 years. So we have $5,000. The B is pretty easy to simplify in this case. And so is the exponent. And we are going to wind up with, after 7 years, $7,518.15. Okay? Alright, monthly. It's the exact same formula. The amount is going to equal the initial value, 100% of what we had, plus 6%. But we're doing this every month. So we're going to divide that 6% by 12. And that's the portion of the full percent we're going to get every month. And we're going to do that 12 times 7 times, which is 84 times we're going to do it throughout the 7 years. And this time we get $7,601.85. Something you should notice, because we're doing it every year, or every month this time, and then we're earning interest on that interest. It happens a little more often. We get a little more money this way. It's also why credit cards do it every month, so that way they can charge you a little more money. All right, next thing we want to look at is E. E is the base for continuous growth. Hopefully I'll talk about this in class, but basically what happens is when you're studying interest, you look at what happened if they compounded $1 at 100% and compounded at the end of the year. And then they looked at what happens, okay, what if we do it every month, and then every week, and then every day, and then every hour, and then every minute. And what happens is, yes, you're going to get a little more every time you change the amount of time down. What they noticed was, at the same time, you might be making more, but each time you go up, you're going up by a smaller amount. So eventually it's going to top off at some value. That value is 2.71828, etc. going on. It's an irrational number like pi. It'll keep on going forever, but it will never set up a repeating pattern either. Okay? Pi shows up, or not pi, E shows up in a lot of interesting places in mathematics, and hopefully you guys stick with math long enough that you get to see more of them. But for now, we're just using it as the base for continuous growth. We're doing that. E is programmed into most calculators. You can find that. So you should look at that, try to do e to the fourth power real quick, and you should get 54.5982 if you round it to 4 decimal places. And that's just to make sure you're using the buttons correctly, so you don't miss any of your problems because of that. Continuous growth. Suppose we have an account that is always making money. Not every hour, not every minute, not even every second. It is just always compounding money. The variables are all the same as they were before. A is the amount of the account, P is the principal, your initial value, R is still your interest rate in decimal, time is still time in years, T is still time in years. The only difference is R is now up in the exponent, and the base has been replaced by E, because it's compounded continuously. That's the key word there. And then here's an example. We're investing $1,050 at 5.5% compounded continuously for 5 years. We know to use this formula. PERT is how people tend to remember it. PE to the RT. We know to use that one because right there, compounded continuously. Initial value was 1,050. E 0.055 is 5.5% as a decimal times 5 years. Head over to the calculator. Power. $1,382.36. And that's how that works. Not only does this work for interest, but other types of continuous growth. A nautilus is a type of sea creature, and its shell. Let's suppose it starts, we get it as a baby at 1 centimeter. That's growing 15% annually. We went on the radius in 10 years. Stuff really grows continuously. It doesn't just sit there at the same size and at the end of the year just magically get bigger. It's always growing. So, the size of the shell is y equals the initial value, which is 1, times e to the 0.15 times 10 years power. And at the end of those 10 years, our little beastie's shell will have a radius of 4.48. The homework assignment that goes with this is page 434, those numbers. One thing to keep in mind, a few of these are stuff we've done together in class, not on the video. So hopefully you were there and paying attention. All right, let's do it. Thank you.